And our next speaker is Onur Danacı, if I'm not wrong. Yeah, and he's I think he's in Netherlands now, right?
Like, yes. So like I made this work I'm presenting like while I was in IBM HBCU Quantum Center at University of Illinois Chicago. But right now I'm a postdoc in Applied Quantum Algorithms Institute in Leiden University.
Okay, yeah. And title of his talk is ManQala. I think engineering quantum states via a ManQala game on real quantum board. Please.
Thanks for the kind introduction, Silay. So let me go ahead really quick because it's pretty loaded. So this is actually a slide tailored for the most of the Turkish audience. Like in Istanbul, you have the street vendors, especially in island ferries, and like they make grandiose statements about their products while marketing their products. So in a sense, like I'm going to make the same. So like this ManQala thing is started as a quantum game, but it snowballed into something really digital quantum simulations and like end up being a quantum control protocol or algorithm. So first, I'll be giving you some heads up about the linear algebraic formulation of this classical solitaire game, a solitaire ManQala game, and like its gameplay and like the underlying physics to it, and give you some examples. And then I will tie this up. How can we simulate this in digital quantum computers? And lastly, I'll be talking about this this whole idea being distilled into some quantum state engineering algorithm. And I'll be giving you some results. So what is this ManQala game? This original ManQala game is a West African game. And I think there are variants everywhere around the world, like in Middle East too. In this game, like each player has like this sites called pits. And in these pits, you have a given number of stones, and like the actions you are allowed to do are like picking. And so you pick, let's say you pick 4 stones from this AQ, and you can do solving. And in the solve move, like you need to dump 1 seed at a time into the subsequent sites. And there's also like the single player version of this ManQala game. And in particular, there's this thing which is widely studied, this thing called Chukayon. This is studied in combinatorial optimization because like its moves are mathematically very rigid. So like in this game, like there are only some possible winnable Chukayon boards, and for these boards, like there's the moves you can make are highly restricted, and there are some heuristics to it. For example, like if you need to always play your stone which is closest to your Ruma, and the point is, by the way, like getting all your stones in here. And but let's say in some configurations you can't win because you would be overshooting it. And in a sense, like we can formulate this classical game in a linear algebraic fashion. In that case, like you would represent each of these pits by using one hot encoding. In other words, like you would represent the number of stones in each of these pits using standard direction vectors. And for example, let's say Ruma has like initially 0 stones, meaning that like you would represent this like E1 having like 1 0 0 0, and then like having different sites, you can just represent by using tensor products. And you can represent your action of like picking by using this permutation matrices. And these are basically classical analog of raising and annihilation, creation and annihilation operators. You would be picking n stones from this and dumping it to there, and then you would be picking n minus stones over there and dumping over there, so on and so forth. You get your solving move. But if you want to have the quantum mechanical analog of this, you don't have this access to this information of like a number of stones usually, so that you can't just do it like pick n, dump n minus 1, etc. Because in a sense, like once you take the cover off, like you are killing some information, like you are killing the Schrödinger's cat. And that's why we need to have control knobs which are coherent, reversible, and unitary. And we can represent this game and we can play this game in some bosonic systems with like quadratic bosonic Hamiltonians. For example, for coupled waveguides into integrated photonics, or like the cold atoms with Bose-Hubbard models without self-interaction. And to be coherent with the game, like we first study like this two-side bosonic couplings. In this case, like let's say you have n equals two stones in this, and you have like m equals 2, you have two sides. And in this case, like basically evolving the system requires diagonalization of this r dimensional, which is n plus m minus 1 choose n dimensional Hilbert space, and it gets immediately huge by the way, like as soon as you have more sides and or more stones. And but like this is actually very well behaving in if you are only looking at the number of stones, expectation values in Heisenberg picture, because this is easily diagonalizable. And once you diagonalize this Hamiltonian, you get your eigenenergies and eigenstates and it's Green's function, so that like you have your equations of motion for the side populations. And in a sense, like we can study some domains like of durations, meaning that let's say you if you want to you want your system, your two side to hop lowercase n stones left or right, it needs to evolve for this duration. But if this duration is this duration function is if it is imaginary or non-analytic, then actually you can't access to that state using unitary evolution. And like there are some characteristics domains. Let's say if you evolve this for pi over 4, you would have like half of the total number of particles in each side. And like if you have pi half, you just permute the side number, side populations. And let me give you an example of, for example, this third winnable board. And let's say if you were to control this using the two-side interactions. And just to be consistent with this classical game, what you would do is that like you would first move this to the left by permitting the numbers by using this two-side interaction of pi half. And then you would be taking this two sides, so two particles over there as well, and then one more. And over here, once you reach this of like 2, 1, 0, and you want to end up in 3, 0, 0, you can't no more go with unitary moves. That's why actually what you could do is that like you would evolve this state into such a state for duration of this very specific duration, such that like the probability of observing the target state is maximized. Then you make a projected measurement. So it is probabilistic. And the way you would simulate the system is like, let's say in your computer, like it's easy unless the dimensions are not too big. It's like you would do exact diagonalization like in this truncated Hilbert spaces, and in this d-dimensional Hilbert spaces, you get your creation annihilation operators as matrices, and these d-dimensional matrices also can be represented by n qubits, and so you have dimensional 2 to the power of n. And but like it gets and you need to have some sort of encoding. Like for simulating fermions, this is much more well behaving, but for bosons, it's, as you see, it's already very nasty. To simulate this hopping Hamiltonian, you need to have all this sum of Paulis. And if you want to take the exponential of this, then you need to do Suzuki-Schroeder decomposition, and like the sum terms become product of exponentials. And each of these exponential terms are actually in this circuit form with some Clifford gates and like some entangling ladders and a single qubit rotations. And I have already like, I don't know, like 60 term or something. And then like, if you concatenate them, it is gigantic, and like you can do all the over-the-top notch circuit optimization, and you still end up with 125 gates and 59 CNOTs. So this can't be done in a NISQ era quantum computer. That's why for the remainder of the talk, I'll be just doing simulations of this. And so like the game in a digital quantum computer is something like this. So you represent each of this bosonic site with using two qubits. And so this is your Ruma, your first bit and second bit. And initially this has 0 stones, meaning that like this is 0, 0 in standard binary encoding is 0, 0, 1 is just 1 in standard binary encoding, and a 1, 0 is like 2, and you want to have this as 1, 1, so that it is 3 and you win. And this unitary moves, like two-side unitaries, become like this 4-qubit interactions. And these are like the old unitaries, and then you evolve it. And you can also see it in this form. Like initially, like with 100% probability, we are in this Fock state, and with the first move, we go to this one, and to this one, and to this one, and then we evolve it in such a way that like the probability of winning the game is maximized. It is in a sense a board like this. So with 4/9 probability, you have 3, 0, 0, you win the game. With 2/9 probability, you have 0, 3, 0. You are only one unitary move away from winning the game. And with 3/9 probability, actually, you go 2 steps back. And actually, like as soon as you evolve this your system into that optimal state, like you make a projective measurement and you store your information somewhere, like in a classical bit, for example. And depending on like what you read, conditionally you make this unitary or you make this unitary, and then you do it again until convergence, until you hit the target state. In a sense, as a quantum state engineering strategy, let me just represent this using this nice looking circuit diagram. Again, like in ManQala, you start with all these deterministic unitaries until it is completely inevitable. Then only then you make this projection measurements, you collapse it, and depending on this mid-measurement results, like on condition of that, like you then do some other unitaries, and then you collapse it again until convergence. Obviously, I'm not the first one to study this. Before me, like there were people coming up with this greedy probabilistic search algorithm to control this Bose-Hubbard quantum systems. Which one? The first one was called fumes, and in these fumes, everything is probabilistic. Like so, you drive your system to this optimal point, then collapse it. And depending on the results, you do some conditional move, and then collapse it again, and collapse it again, collapse it again. So for this turbinable board, it's something like this. Like so, you evolve it for some time, you make a mid-circuit measurement, and depending on the results, there's a lot of conditions, and do it again. But some people improve this, and the idea is like this Zeno locking. So what is Zeno locking? In the regular quantum Zeno effect, you would be constantly observing a quantum system while it's and through this projective measurements while the unitary time evolution is running, so that you halt its evolution in time. But there is also this idea of Zeno subspaces, and in the Zeno subspaces, you again have this unitary time evolution running on the background. But instead of like the global measurements of like all the system, you make partial measurements only in the subsystem. Such that like you effectively have a different time evolution. You have the Zeno subspace, like in a sense, like you have this block diagonal Hilbert space, like running each of them running independently. And like in our case, like let's say if you keep making this measurements and dumping this information somewhere, your 3-side interactions become effectively 2-side, which what we were doing for ManQala. And in a sense, like you get this effective Zeno Hamiltonian for a list of projections. And in a sense, like your, let's say, if you evolve for pi half, for 2-side interaction, you would, starting from this, you would end up in here. And this is the simulation of Zeno subspaces, you end up in the same place. And in practice, in Zeno fumes, it means that like you again have like this fumes conditions, but like for some certain states where you Zeno lock it, you have different things. Like for this 3-0-0 system, let's say your sub lattices and the lattice and some of the other lattices have the exact target number of particles in it, then you lock them so that like you only evolve and you search in this smaller search space, basically. But like this is also another joke targeting Turkish audience. Like there's this Turkish saying like you would lie under a pear tree and wait, idle wait and passively wait for the fruit to fall in your mouth. Like in a sense, like in Z films, yes, like we are going into this smaller search space, the xenologue search space, but we still do this passively, like through this random greedy search. Like what if we actively drive our system over there? And like this is what we do with ManQala actually. So like this is the one of the stochastic trajectories of ManQala. Like you start with like 2, 1, 0, and then like and we evolve this only through like unitary time evolution until it is absolutely necessary that like we do some projective measurements and we do it over there. Then we get our target state. And but like for fumes, you evolve, bam, you make a measurement, evolve, make a measurement, evolve, make a measurement, and like it converges much slower with a much higher volatility. And like with in Z fumes, it's the same intuition, but like as soon as you hit this xeno subspace, like you lock it. This is 0, you lock it, and you only do 2 site interactions over there. It converges slightly faster. But like, yeah, as the statistics show, like over 1,000 shots, this ManQala is much more reliable. And actually, we can even, and this is the now 1,000 trajectories, stochastic trajectories, like Monte Carlo simulation for all of this. And this is if you repeat only twice, and this is like if you keep repeating indefinitely until convergence. And what we see is that like over here, like if our metric is just fidelity, it looks like ManQala is doing nothing until making some measurement over there. And that's why like we don't have any shades over there. It's totally deterministic. So this is ManQala, and this is what I call modified ManQala. Like when we relax some assumptions about ManQala, it converges faster. It's the same statistics. And it is actually more apparent if I use some other distance metric. This is what we call boson hopping distance or bosonic distance. So it is this idea that like, in a sense, like the sites, for example, 300, 030, and 003 are all orthogonal to each other. But in a sense, like the 030 is closer to 300 because you are only hopping only 3 particles to the left, while for the latter, you are hopping 6 particles. And in a sense, this is what we think an analog to Hamming distance for bosons, like particle hopping distance. And it is more apparent over there because over there, like actually with ManQala, we are actually driving our system towards the end goal. Then we make a measurement. And instead of like keep making measurements and stochastic converging it. So in a sense, like this Z fumes and this modified ManQala converges on almost at the same time. But like the Z fumes has like average standard deviation for this distance of like 17%, while like ManQala is around like 6-7%. And I'm not going to go over this. Like this, in a sense, like this mod ManQala X is a very sophisticated combinatorial optimization problem. We are not able to solve it yet. We are leaving it to the computer science and mathematicians coming after us. But like the whole point is this, like in, let's say you are initially given this system, and let's say you want to drive the system into this target state of like 1, 1, 1, 1, 1. This is what the people in the literature called mod insulator state, and not the phase. And like you, let's say you collapse this, and then like it's some probability you have like 3, 1, 0, 1, 0, and like it's some probability 1, 3, 0, 1, 0. And what the heuristic is this, like, so like coming distilled from this actual ManQala game, like you permute the site populations using like this pi half or square root of 2 pi half interactions deterministically, such that like you bring the sublattice populations, you actively drive the sublattice populations into the one of the target state. I mean, over here, like now I have 1 over there, just like the 1 over there. Now I have 1 over there, just like the 1 over there. Such that, and like for this, and I have another sublattice over here. And like for this, like the target sublattice population is 3. And I have also have 3. Instead of like searching this gigantic space, like I'm doing Z fumes only on this. And like for larger systems, actually, it is even more, it makes even more sense. And for this one to like just flip this population so that, and after you xenolock this by constantly observing them, and then running the Z fumes only in this small subspace, you reach much faster and much more deterministic. Or and the latest example is like the let's say we start.
Onur,
yeah, sorry.
Could you please wrap it up?
And this is the last slide, right?
Okay.
And let's say again, you start with this superfluid state, and then you can decompose it into like mini of this. And the point is, let's say I am driving through these determinate pulses in such a way that I have this sublattice populations, like for example over here, like I have 2, 1, 2, just like 2, 1, 2, or like 1, 1, 3, just like 1, 1, 3 over here, so that we can do Z fumes over there. And what we found, just like our predecessors, games and control problems are akin to each other. You can start writing a paper on one and then end up in the other. And these game intuitions can be distilled and used as control heuristics. And also this bosonic dynamics with non-demolition measurements can be simulated in this digital quantum computers with measurements. But for the future work, maybe let's dump this standard, so this digital quantum computing altogether and use native bosons, for example, in the superconducting cavities, or we can create VQEs, variational quantum eigensolver algorithm to create the super fluid states and the others, or we could just fast forward the quantum dynamics and everything can be simulated in the actual quantum hardware. So thank you for your time listening to me, and I could take your questions.
Okay, thank you, Onur. We can have one quick question if there are any. Let me check. Okay, I guess we don't have any questions. And maybe I can ask, you said you assume there's no interactions, right? On-site interactions.
Yeah. Mm-hmm.
But in the interacting case, it would blow everything, or?
This is a good question. So this is one of the cases studied by one of the previous groups. What they also used in order to gauge this transformation, they used that self-interaction is a adiabatic control knob. So because by slowly tuning, you can also get this, for example, starting from superfluid and then end up in the other one. Mm-hmm. But they found it is much less deterministic. I mean, the overall population is going there, but most of the time you don't end up there. And another idea for the future work is that to solve this combinatorial optimization problem, let's say we are using some AI algorithms like reinforcement learning, and we could add this as a control knob to let's say you are doing this coherent interactions and measurements and measurement back action. Maybe also you can also use this tuning this self interaction as a control knob as well. So yeah, this can be doable.
Okay, thank you, Onur, and thanks again.